Today we're looking at reversing everything we've done with parallel lines so far. Now we are going to know that lines are parallel and try and figure out the angles that are associated with those parallel lines. Good news is it's a complete opposite of what we've been working with. So if you know that they're parallel, now you know alternate interior angles are congruent. You also know alternate exterior angles are congruent, and same with corresponding angles. Similarly, we know that same side interior angles are supplementary, and that the same side exterior angles are supplementary. We had a theorem in the last section that talked about if two lines were perpendicular to the same line, then they were parallel. Now we have the reverse. It says in a plane, so all of our lines are in the same flat surface, a line is perpendicular to one of two parallel lines, then it's got to be perpendicular to the other one as well. Now I told you guys that basically that last one was just kind of a nice thing to know. But if we have this diagram here and we know that these are parallel lines, so I'm going to say that L is parallel to M, then if this line N is perpendicular to L, if we use the fact that our lines are parallel, then any corresponding angles are going to be congruent. I can also say that this is a 90-degree angle, which means that N is now perpendicular to M. That's how that theorem works. And then the last one, it says if two lines are parallel to a third line, then they're parallel to each other. So we have a line here, and if we have a third line that's parallel to both, we'll call these L and M again. To both of these, then it could be something in the middle, or it might be above one of them. But if it's parallel to one of these lines, then it also has to be parallel to the other one as well. And we're going to use that later on in a problem we call Crook problems, which is my favorite problem of the year. So in for a treat today. Alright, so here's our first example. It says EX is parallel to OP and EO is parallel to XP. That's given information. So before I get too far, I'm going to highlight those lines. I'm going to go with these guys in the purplish, pinkish color. So I've got my line EX and I've got my other line OP. And I'm going to highlight the other one in green. So we'll call this EO. And XP. Now you'll notice in the middle of all that we have this segment EP. That's our transversal for both the lines EX and OP, and also for EO and XP. And that seems like it's going to be a really important segment when we get into the proof. So we want to show that EXP and POE are congruent triangles. Well, something that should be pretty obvious anyway is that we can show that those segments are the same. So if I were to start off this proof, I could say in step 2 that EP is congruent to itself. And that's by the reflexive property. So thinking about the different types of angles that we have, we know that everything is inside the lines. I don't see anything outside. I don't see any corresponding angles, alternate exterior, same side exterior. I've got one of two choices. Knowing that these lines are parallel is going to tell me that same side interior angles are supplementary, and it can also tell me that alternate interior angles are congruent. So looking at X, if we go from X to E and then follow it down to P and across to O, you've got that Z shape. That Z shape is going to form alternate interior angles. So I know that actually these angles are congruent. Similarly, if I go down the green lines, I start at O, go to E, follow it to P, which takes me up to X. I've got that N or Z shape, which is also alternate interior angles, which tells me now that these angles are congruent as well. Now I have enough information, because I have an angle, a side, and an angle, to say that the triangles are congruent by ASA. But before I do that, I need to state that I've got those congruent angles I just marked up. Angle XEP congruent to OPE. Angle XPE congruent to OEP. So I started off with having parallel lines, which gives me alternate interior angles congruent. We've done the reverse. We said if we had alternate interior angles congruent, then that gave us parallel. So if you have that relationship down, the reverse is just not that difficult. You're just starting off with parallel and ending with alternate interior angles congruent. So in step 4, we had enough information that we said that the triangles are congruent. So triangle EXP congruent to triangle POE. And that's ASA. Now let's take a look at an algebra-based problem. And this is what's called a crook problem. So the given information, oops, I guess we need the names here, don't we? Is that A and B are parallel lines. And we want to find the measurement of angle 1. So we're using that last theorem we talked about, that if two lines are parallel, there's another line that we can draw that's going to be parallel to both of those. So I'm going to draw in an auxiliary line that's going to go through this point here. So let's see if we can do this correctly. Pretty close. This new line that we drew in, let's call it C, is parallel to both A and B. Now if they're parallel, that means that any angle relationships that we have that we know have to be true will apply. So in this case, if I have a 40-degree angle, let me highlight that 40-degree angle. And if I extended it, now I've got that F shape. So that means that those angles are corresponding. So if this part's 40 degrees, then the top part of 86 is 40 degrees as well. Now from there, I want to figure out what's this missing piece, because that'll help me find angle 1. So I'm going to take 86, take the 40 away that I've used up, which gives me 46. Now in relation to line C and line B, angle 1 is same side interior. They're both between the lines and on the same side of the transversal, which means to find angle 1, I'm going to take 180 minus 46, and that's going to give me 134 degrees. And that's a crook problem. We call it a crook problem because there's a crook in the line. It bends. That's why.